All right, so let's talk about boiling point elevation and freezing point depression. Both of these fall under the general category colligative properties. Colligative properties are properties of solutions that arise from the interaction of solute particles with the solvent, and the amount of property that you'll see, or the degree of intensity, is based on the number of solute particles. Not so much on the identity of what they are, but just how many there are. Okay? Boiling point elevation. Elevation means to rise, so we're talking about raising the boiling point of a liquid. All right, we already know this. Non-volatile solute lowers the vapor pressure. Solute particles interfere with solvent particles getting into the vapor. And so it takes more energy, therefore, to get those particles into the vapor. And since you have to add more energy, the temperature of the solution will go up before you can reach the boiling point. So remember, you're trying to get the vapor pressure of a solution equal to atmospheric pressure in order for it to boil. If you have particles in that mixture, in that liquid, that are interfering with that, they're preventing liquid molecules from getting into the vapor, then it means you have to add more energy to get those same number of particles into the vapor, to get your vapor pressure equal to atmospheric pressure. That means that your liquid is going to boil at a higher temperature. Okay? So a non-volatile solvent, a solute, elevates the boiling point of the solvent. The amount of elevation, how high the boiling point will change, depends on the concentration, in other words, the number of particles of the solute. Okay? It's determined by this particular equation, delta T, meaning the change in temperature from what it should be to what it now is equal to this Kb, which is the boiling point elevation constant, times the molality of the solute. Okay? Molality will be discussed in just a minute. So here's a little graphic showing you what this might look like. We see something similar happening with freezing point that we'll talk about in just a second. Okay, the vapor pressure of pure water, vapor pressure of the solution. And as we move over here towards the right-hand side, you'll see that it requires more energy to get the vapor pressure of the solution to equal atmospheric pressure. And that means that we've got a little bit of change of temperature, a rise of temperature. Okay, we see the same but sort of opposite effect with freezing. Since at the freezing point, the vapor pressure of the solid and liquid are equal, right? If we have a non-volatile solute, it lowers the vapor pressure. And that means that you need less energy added to decrease the vapor pressure to the same as that of the solid. It takes less energy to cause the same vapor pressure necessary to be solid. What that means is that a non-volatile solute depresses the freezing point. It lowers the freezing point. This is why we put salt on ice in the wintertime, okay? Because the salt is the solute. It's non-volatile, sodium chloride. And it lowers the vapor pressure of liquid water such that it takes less energy to get the solid to melt, or to get the liquid to freeze. It's at a lower temperature. It'll freeze at a lower temperature. Now, of course, in Wisconsin, we have temperatures that are so cold that it doesn't matter. That the temperature is so low that it doesn't matter how much salt we put on there. It'll never lower the vapor pressure enough that it'll keep the liquid from freezing. But under normal conditions, when the temperature is around 0 degrees, or a little bit above 0 or a little bit below 0, you can usually add some salt, and that will lower the vapor pressure to the point where the liquid won't freeze because its vapor pressure will be too high. And again, it depends on concentration. Similar equation, delta T is equal to Kf. K is a constant. Kf is the freezing point depression constant. And molality, little m is molality, not mass, molality. Okay, we'll talk about what that means in just a second. So here's some examples of some boiling point elevation constants, Kb, and freezing point depression constants, Kf, for several solvents. It gives you the value of the constant. It's in degrees times kilograms over moles. Okay? And we'll understand a little bit more about why the units are that way. So for water, it's 0.51. For carbon tet, it's 5.03. So you can see sort of that water, with its very high intermolecular forces, is a pretty low Kb value and pretty low Kf value. Okay. Okay, so let's take a look at an example. We're making a solution of glucose and water. We've got 18 grams of glucose, 150 grams of water. If this were pure water, the boiling point of pure water would be 100 degrees. But because we've added a solute to it, the boiling point's higher than it should be, 100.34 degrees. We have Kb for this solvent, for water. 0.51. And what we're interested in is finding the molar mass of glucose. Now, in looking at this problem initially, you might say, wait, how the heck are we supposed to find the molar mass of glucose? Let's think about what we need in order to find the molar mass of glucose. We need grams per mole, right? Well, we have grams of glucose, 18 grams. What we need is how many moles of glucose do we have here, okay? And then we should be able to figure out the molar mass. All right, so there's some things we have to take into account. First is that we're talking about boiling point elevation. That's delta T is equal to Kb times m. Delta T is the difference in boiling points from where it should be, the pure solvent, to where it now is with the solute in it. Kb is the boiling point elevation constant, which is given to us in the problem, and m is molality of the solute, and we're going to have to talk about that. Okay. First, let's fill in some information. Delta T is equal to T final minus T initial. T final was 100.34. That's what the boiling point now is. And it should be 100, so minus that we get 0.34. Okay? And that's going to be equal to the Kb value, which was given at 0.51, times this m, this molality, whatever that means. Okay? So we're going to solve for molality. All right? Let's do that. Molality is going to be just the 0.34 over 0.51. We're just using algebra here, right? We're moving the 0.51 to the other side by dividing. Okay, so the molality is 0.67 moles per kilogram. Look at how the units will cancel out. So molality is the number of moles of solute divided by the number of kilograms of solvent. Not solution, but solvent. So if we had 1 kilogram of water that we were mixing this into, then we'd be all set. We'd know what our number of moles is. But because we don't have a kilogram. We have 150 grams of water that we've dissolved this stuff into. That's 0.1500 kilograms. So molality is the number of moles of solute divided by the number of kilograms of solvent. In this case, we're going to try to figure out how many moles of glucose we have here. Okay? We have 0.1500 kilograms of water, 150 grams. All right, so we're going to solve for N. N is 0.67, which is the molality, times the mass of solvent. And that gives us 0.10 moles. Okay? So we have 0.10 moles of glucose in this case. And we have 18 grams of glucose. And since molar mass is grams over moles, we divide 18 grams by 0.10 moles. And we have 180 grams per mole. That's the molar mass. Okay? So molality can be used to find things like number of moles because it's related to number of moles. So is molarity, but when we're talking about things like creating solutions and colligative properties, we're going to want to use molality to do our calculations. All right, here's another one. What mass of C2H6O2? C2H6O2 is something called ethylene glycol. The molar mass of it is 62.1 grams per mole. And we're going to add this to 10 liters of water. We want to make a solution that freezes at minus 23.3 degrees Celsius. The density of the solution will be 1 gram per mole, and the boiling point constant, Kb, is 1.86 Celsius per kilogram per mole. Okay? I'm sorry, that should be the freezing point constant. Okay. All right, so delta T is equal to Kf times m, moles solute. We know what delta T is. It's negative 23 minus 0, so negative 23 is our delta T value. We're lowering the freezing point by 23.3 degrees. And that's equal to Kf, which is given, 1.86, and molality, which we don't have again, but we can sort of use some information to get that. Okay? So we rearrange. Molality of the solute is going to be negative 23.3 degrees Celsius over 1.86 degrees Celsius times kilograms over moles. Degrees Celsius will cancel. You'll have 1 over kilograms per moles. That'll flip. You get 12.5 moles per kilogram. That is the molality of the solute. Okay, that's the number of moles of solute per kilogram of solution. We don't have a kilogram of solution here. We have 10 liters. 10 liters times 1,000 milliliters per liter times 1 gram per 100 milliliters, the density, times 1 kilogram over 1,000 grams is 10 kilograms. So we have 10 kilograms of water, and the molality is 12.5. So 10 kilograms of water times the molality, which is 12.5 moles per kilogram, gives us the number of moles of antifreeze of ethylene glycol to use, and then we use the molar mass of that, 62.1 grams per mole, and that'll tell us that we need 7,760 grams of C2H6O2 in order to lower the freezing point of that much water, 10 liters of water by 23 degrees. That's a lot of ethylene glycol. Okay? One of the other properties of solutions is something called osmotic pressure. So in order for osmotic pressure to be measured, you need something called a semi-permeable membrane. Semi-permeable membrane is a partition that allows solvent particles to pass through, but not solute particles. It's usually based on size. Okay? It separates out. You can use it to separate out a solution from the solvent. Okay? Here are some examples of how this works. So we have on one side of this U tube over here, we have a pure solvent. On the other side, we have solution, and we have the semi-permeable membrane before it, now between them. Now, what's going to happen is that the solvent particles are going to go through the membrane, and they're going to go over towards the side that has the solute in it. The reason this happens is because the water, the solvent particles, are trying to equalize out the concentrations. The concentrations on either side of the membrane need to be the same, or they're trying to be the same. And so the best way to make the concentration of the solution on the right equal to the concentration of the pure solvent is to lower it. And the way you can lower concentration is by adding more solvent. So the solvent is going to diffuse through the membrane away from the pure solvent and into the side of the solution. And that's going to cause the volume on that side of the tube to go up. Now, at some point, gravity is going to come into play and it's going to stop. And if you measure the distance, the difference in heights of the left tube and the right tube, that difference will be the osmotic pressure. Okay? Now, it's a little sort of difficult to measure because we're not dealing in mercury, so we can't measure in millimeters of mercury or torr. So the best way to do this then is to sort of apply a pressure to the side that's higher and force it back so that they're equal, and then measure how much pressure it took to force it back, because the pressure that it takes to force it back is equal to how much pressure of the solution was providing. Okay? Osmosis is the flow of solvent through a semi-permeable membrane. Okay? It's trying to get to equilibrium. The system is at equilibrium when the concentration on either side of the membrane are as close to equal as they can be. All right? But because of that, because solvent is going through the membrane into the side with solute, it's going to change the water levels. Okay? And that has to do with something called hydrostatic pressure. All right? So that the hydrostatic pressure is this tendency for the solvent particles to move towards the side that has the solute. What we then can do is we can measure how much it takes to push it back to normal, how much pressure it takes to push it back, to push the water levels back equal, and that's called osmotic pressure. It's represented by a capital letter pi, which looks like sort of almost 3/4 of a rectangle. And pi is equal to mRT, okay, where m is the molarity, concentration moles per liter of the solution. R is the gas law constant, and T is the temperature in kelvins. Okay, so we apply the pressure to stop osmosis, and we measure that pressure, and that's our osmotic pressure. That's the way it's measured typically. Okay, so if there were no pressure on the right-hand side, then the liquid level on that side would go up. But we apply a pressure to stop it from happening, and we measure that pressure, and that's how we measure osmotic pressure. Now, we don't generally do this in the lab very much, but we can use it in calculations. Okay, so here we go. We have 1.00 times 10 to the negative third grams of a protein is mixed with water to make 1 milliliter of solution. The osmotic pressure is 1.12 torr at 25 degrees Celsius. Find the molar mass of this protein. All right, again, we're looking for molar mass here, but part of osmotic pressure is molarity, right? And that contains the moles term that we need. All right, so we've got pi is equal to mRT. All right, we don't know what m is, capital M, right? But we do know what R is, and we do know what T is in Kelvin. We do have to convert our pressure to atmospheres if we want to use 0.82. That should be 0.08206. We'd have to convert our pressure to atmospheres, so we can do that just by dividing by 760. Okay, we get the molarity of the solution is 0.601 times 10 to the minus fifth moles per liter. That's the molarity. All right, so now we know how many moles of protein we have. And in the problem, we know how many grams of protein we had. And so molar mass is grams over moles. So we're going to need to change our milliliters of solution to liters because we're working in liters. And we can get 6.01 times 10 to the minus 8 moles of protein. Molar mass is mass over moles. So 1.00 times 10 to the minus 3 grams of protein divided by 6.01 times 10 to the minus 8 moles of protein is 1.66 times 10 to the 4th grams per mole. That's 1,660 grams per mole of this protein. Proteins, by the way, if you hadn't figured this out by now, are ginormous molecules. They're huge. And so their molar masses are just way off the charts.